Hi, Basic Calc. These are your day 124 notes. Today, we are looking at an introduction into our last chapter on vectors. So this is chapter 12 right here. Hopefully, a lot of what we see today in the beginning will be a review of what you learned in Pre-Calc Honors, okay? But if there's a couple of refresher things that we have to pay attention to, of course, we'll do that. So to get started, what is a vector? A vector is a mathematical quantity with magnitude and direction, just like our favorite character from Despicable Me says. Perhaps we will watch that post AP, because why not? All right, so what do we have as an example? If we have a wind blowing at 20 miles per hour at north 30 degrees east, well, we've got a certain magnitude or force behind that. And then this is the direction that the vector would be pointed in. So if we start with a line, let's say due north, and we rotate 30 degrees east of that, we have that this vector right here is the wind vector that we're talking about that has an initial point right here. And the magnitude, which in our case is going to represent the length of that vector, is going to be 20 miles per hour. And then over here is the terminal or the endpoint of the vector. Because it has that specific length, the arrow is just there to indicate direction. But really, it doesn't imply that this goes on forever and ever. And if you're familiar with vectors, this is something that should be just fine for you. But if you haven't seen vectors in a while, because you're not in physics, then certainly we'd want to make a point here to say this is a point where we end. Okay, and the vector has a specific length. The arrow is just there to indicate direction. So from there, some quick notation things. We can use just calling it straight out, vector K. More commonly, you'll see an arrow drawn over the top of either a lowercase letter to represent the vector, or you might see it written in terms of 2 points. If we have an initial point and a terminal point defined, A and B, the vector might be written as vector AB. So for a quick example here, if we were to, let's say, have an initial point at 0, 0, and let's say a terminal point at 3, 4. What might that look like? Well, if we go 3 to the right and 4 up to plot that terminal point right there, we have the following vector. And the way we can represent that vector V is in terms of its horizontal and vertical components. So in general, the horizontal component would be represented by V1 right here. And then the vertical component would be represented by V2. A common notation for vectors is these triangular brackets here. Sometimes in the AP, you'll see parentheses used almost as if it were a coordinate point. So we just have to read carefully to know if they look like coordinates, are they really representing vectors there? All right, so you'll see both notations used. But according to the terminal point being at 3, 4, given that the initial point was at the origin, this vector in particular could be represented as 3, 4, the horizontal component and then the vertical component. All right, how do we find the length of the vector? So length or magnitude of the vector is notationally with our double bars here. And it's basically an application of Pythagorean theorem, right? So to find the length of this piece, it's going to be the square root of the horizontal component squared plus the vertical component squared. And that, of course, direct application of Pythag there. All right, so in this case, if we use the example above, the length of the vector or the magnitude of the vector would be 3 squared plus 4 squared. And 9 plus 16 is 25. So the length of that vector, its magnitude is 5. Something that might sound familiar from last year in Pre-Calc Honors is talking about a unit vector. So a unit vector is a vector whose length is 1. So the example says find a unit vector in the same direction as 3, 4. If it doesn't say same direction, opposite direction would just be negating your final answer. But a unit vector in general, to get it to have a length of 1, is to take the components of the vector and divide by the magnitude of the vector. That will guarantee that your vector has a length of 1. So in the last example that we had with our vector 3, 4, if I divide each component by the magnitude of 5, we result in the unit vector 3/5, 4/5. And if you were to find the magnitude here, or the length, you would determine that in the end, the length of this vector is 1. Okay. So in case unit vectors ever come up in context, it's just taking the vector and dividing by its magnitude to get a vector of length 1. Some special vectors that you might be accustomed to and familiar with are called the basis vectors. Okay, so the basis vectors are unit vectors in the horizontal and vertical directions. They're typically represented by the notation I and j there. And every single vector into space can be expressed in terms of these two vectors. So if we go back to our last example where we had the vector 3, 4, we can represent this vector as the following sum. We can say it's 3, 0 plus 4, 0. Okay, if we find the sum of those vectors, oops, sorry, let me switch that around. Actually, you know what? Not 4, 0. We need the vertical component to be 4. A little whiteout can help us here. Okay, so 3, 0 plus 0, 4. The sum of these vectors would get me back to 3, 4. And if you take out the scalar of 3 here and write it as 3 times 1, 0 plus over here 4 times 0, 1, we've broken it down now in terms of those basis vectors. So the original vector 3, 4 could be written as 3i plus 4j. So you'll see vectors represented in a variety of contexts, knowing that this is the horizontal component, that's the vertical component, based on the original basis vectors for I and j that are defined. Okay, so you're going to see both notations used pretty much interchangeably throughout this entire vectors unit, so we got to make sure we're familiar with both. Okay, next thing we're going to talk about is a little calculus with vectors. So it says let x equal x of t and y equal y of t be a pair of parametric equations. For all values of t, we're going to construct the vector r of t that has x of t and y of t as its components. So based on the way that we define this vector r of t, you'll notice that it's written in terms of two functions, x and y of t. So it's starting to have a very parametric feel about it, right? All right, so here's what we've got. R of t would equal, in the basis vector form, x of ti plus y of tj. Or if we like this form better with the triangular braces, it would be of the form x of t comma y of t. And the vector r of t is called a vector valued function. So you'll see that language used at times, a vector valued function. And essentially, if you were to calculate r of 1, it would correspond with this pair of parametrics, whatever x of 1 and y of 1 are. And r of 2 very similarly would be this vector that has horizontal and vertical components defined by x of 2 and y of 2, and so on and so forth. So from there, if you have that picture drawn into your notes, what we're going to do is we're going to look at the example at the bottom there, which is given to us as x equals t squared and y equals 3t. And we're going to take that pair of parametrics and define the vector valued function r of t. So r of t, again, can be written in two ways. If you want to write it in terms of the basis vectors, it would be t squared I plus 3tj. I have a feeling that our preference will be to use triangular braces and say that this is just of the form t squared 3t. And then we can calculate things like, what is the vector value function r at 1, right? So what would be its horizontal and vertical components? Well, it'll be 1 squared, which is 1, and then 3 times 1 is 3. So it's pretty easy to sub in to get our vector value function at specific values of t. We could do this at -2 if we wanted to. So -2 squared would be 4, and then 3 times -2 would be -6. And finally, if we were to do this at 0, we would get 0, 0. Which uniquely is not quite a vector. It would just be a point at that location. Okay, this has no specific magnitude or direction. So if you plot the vector 0, 0, that 0 vector, you're going to wind up getting that it's a point and not a vector at all. The others are vectors in specific directions. Okay, so if we're good with those components, what we're going to move on to now is talking about there's a lot of language here, just kind of building towards finding some derivatives and limits within vectors. So if we have our vector value function defined in the following way, as the parameter t varies, the tip of the vector r of t traces out some sort of curve. which is represented by those parametric equations. So we call C the graph of R of t, and we call R of t the radius or the pointer vector. And I'm not sure how important you'll see that those two words are for the following unit, but in case it comes up in context ever, the radius or the pointer vector for the curve is defined by R of t. So C can be thought of in two ways. It can be thought of as two parametric equations or as one vector valued function of the form R of t. So just know that there's definitely a big connection here between what we did not too long ago with parametrics and what we're now looking at in terms of the horizontal and vertical components of this vector valued function. So now we're going to start bringing in some more calculus here with some limits. So for the limit as t approaches c for some vector valued function R of t, that would just equal the limit as t goes to c for each component individually. And the result of that limit, the sum of these limits, would be some limited value that represents a vector. So some value L, where L is a vector result. So what does this actually mean, that notation? That the limit as t goes to c of R of t equals some vector L? It means that the vector is approaching L in both length and direction as t approaches c. Okay, so as t gets closer and closer to c, we're approaching some vector that has a certain length and is in a certain direction. So for example, if I go back to that last example where R of t equaled t squared and 3t, we can find the limit as t approaches any value. Let's find the limit as t approaches 2 for R of t. So very simply, that's going to be 2 squared, and then for the vertical component, 3 times 2, which would be the vector 4, 6. Okay. So if you want to write this in terms of the basis vectors, just to kind of get used to both notations, 4i plus 6j is another acceptable way of writing that same vector. So just some of the basics to get us started, because now what we're about to get into within vectors is talking about derivatives. Okay. So the derivative of vector valued function, well, here's that limit definition of a derivative, which you probably haven't seen in a little while. But hopefully it's bringing back some good memories. The limit as delta t goes to 0 of R of t plus delta t. Minus R of t over delta t would be the limit definition. And what we're doing is we're taking the slope of that secant line, and as the change in t goes to 0, we're getting closer to the tangent line. And for a quick visual, if you want to include this in your notes below, okay, we have some curve that's defined by R of t. And each of these vectors are drawn to the points along that parametrically defined curve whose horizontal and vertical components are x of t and y of t. Okay, so we can see here that if we want to find the slope at this specific point right here, if we go a certain delta t away, find the slope of that secant line. As delta t approaches 0 and we close in here, the secant line is going to get closer and closer to the tangent line. And what we can see as a follow-up here is that since we have R of t defined as that pair of parametrics, that theorem below defines for us here that if we have R of t is some vector x of ti plus y of tj, then the derivative R prime is just simply the derivative of each of those components. So it's going to be pretty easy for us to be able to find the derivatives of vectors by just finding the derivative of each of the horizontal and vertical pieces. So here's an example of that. If we have R of t equals e to the t squared I plus ln of tj, we can find the derivative of each component and write that as a new vector. So R prime of t in this example would be the derivative of e to the t squared. Just make sure you use chain rule there. So it's going to be e to the t squared times the derivative of that exponent, t squared. So that's 2t e to the t squared. And if we keep this in the basis vector form, that would be the horizontal component I plus derivative of ln t, which is 1 over t j. And that's very simply put, the derivative of this vector valued function. So from there, we could ask you to find things like, what's the derivative at 1, R prime of 1? And that would be if I plug in 1 for these inputs, it would be 2 out front, e to the 1 squared, so that's just 2e And that would be the horizontal component plus, if I plug in 1 here, it would just be plus j, which might be more commonly written as 2e comma 1. And then following from there, if I wanted the magnitude of this specific vector representing the derivative at 1, we know that that would just be the square root of the horizontal component squared and the vertical component squared. So that would look like something of the following form. It would be something like 4e squared plus 1 under the radical. And that will actually come into context later on when we start eventually relating our vectors in terms of position, velocities, accelerations, the magnitude of this derivative, which might represent velocity in certain contexts, is going to have something to do with speed. So we're getting into that in just a little bit. We have to define just a couple of more rules here, including, well, hey, guess what? We have a chain rule. If we can use derivatives within our vectors, we can also apply a chain rule that if we have something of the form du dw, where our vector u is a differentiable function of t, and t is a differentiable function of w, then we can use the chain rule to do du dt times dt dw to get the derivative of the vector u with respect to w. So the thing about this is if we know t equals w squared, I have a feeling a lot of us would probably just replace each t with w squared and then find the derivative of each of those components. And that, of course, is fine. You are allowed to do that. Okay, if you wanted to use this definition of how we wrote chain rule over here, well, we can find du dt and multiply each of those components by dt dw, where t equals w squared. So that would give you the following, that du dw in the end would be the derivative of 3 cos t, which is negative 3 sine t, times the derivative of t with respect to w, which is 2w. Okay, and that's all the horizontal component next to the basis vector I, plus the derivative of the second component, which would be 3 cosine t, times, again, derivative dt w, which is 2w again, j. And cleaning this up a little bit, you would get negative 6w sine t. I'll even write this in our alternate format here. And then finally 6w cosine t. Okay. Now, within our context here of writing this in terms of t, if we're finding the derivative of the vector u with respect to w, we should at this point just make one more quick substitution because we know that t is equivalent to w squared. So just to make sure everything agrees in the end here, okay, we'll replace those t's with w squareds and stop there. I think, to be honest, the easier thing to do, even though I just showed you how to apply this definition of chain rule, is probably from the start, replace the t's with w squareds, and then just make sure that in each case, when you find the derivative of the components, that you account for the chain rule based on whatever's inside the parentheses. Okay. So either way around it, it's up to you. But in the future, I may just sub that in first and then kind of go from there. And well, hey, guess what? If we can find derivatives, we can find integrals as well. So if we have some vector r of t whose components are x of t plus y of t in front of our basis vectors, then the integral would be equivalent to doing the integral of each of those components. So given r of t equals 2t times the basis vector I plus 3t squared j, the integral of r of t is going to equal the integral of 2t dt, and that's going to be next to the basis vector I, plus the integral of 3t squared dt, and that will be the vertical component for j. All right, well, these are pretty easy integrals to calculate. We're just going to get t squared I plus over here, anti-power rule will give you t cubed j. Plus, now we know when we find it, work backwards and find the antiderivative that we have to add on c, but what is c really? C is a vector in this case. Okay, so that's gonna be a little bit different for us, but we'll eventually get used to this where we might even have some initial conditions that would allow us to find the value for the vector c. Okay, so another way that this could be rewritten is since C is a vector, whatever the horizontal component of this vector is, if C, let's say, has components C1 and C2 for horizontal and vertical components, okay? The horizontal component would be added to this horizontal component T squared. So this could be written as T squared plus C1, whatever that might be. And then T cubed would get added on to C2. So that's just another way of thinking about how we would write our final answer here when finding the antiderivative. And in certain examples, when we're given, like I said, some sort of initial condition, we can work backwards and figure out what C1 and C2 are and go from there. So that was just, I think, a little bit of a taste of what we can do with the calculus of vectors, whether it's finding derivatives, antiderivatives. This last page, I think we'll save this for class where we have a practice AP question with some information about vectors. If you want to take a look at it in advance, of course, you may do so. But we'll wind up going over this next time in class and do a little bit of graphing with that as well. So that's it for our quick intro into vectors and the calculus of vectors today. Have a great rest of your day.